we're going to talk about how to jam nonlinear specifications into a linear regression and then call it nonlinear regression. We do this because, as you probably noticed, economists are good at wringing every last bit of juice out of any good idea. Good ideas are rare. We got to squeeze every bit of juice we can get out of them. Linear regressions, OLS, are one of those rare good ideas we want to get a lot of use out of. Now, nonlinear models are generically probably how the world works. Linear model is a simplification, admitting that, we don't know that much, actually. It's a first-order guess. If you remember the Taylor series from calculus, any differentiable function can be approximated within a neighborhood by a linear function. Now, not every function in the world is going to be differentiable. Certainly in your finance class, you'll learn about variables with non-differentiable paths. But for a variety of cases, we're comfortable specifying the relationship should be smooth. The idea of higher-order polynomials sort of spills right out from the Taylor series idea. How do we use a linear regression with a nonlinear term? Well, ordinarily, a multivariate regression sets y equal to beta naught plus beta 1 x1 plus beta 2 x2, etc. But what if for x2 I just move that 2 up and call it x squared? Or any other nonlinear function of x like log x. It works fine. It just goes right on through. It's good. Let's do an example. I regress wage on beta naught plus beta 1 age plus beta 2 age squared, plus other stuff, plus the new error term. Now remember from calculus, how do I find the derivative of y? Or in this case, the derivative of wage as age increases. Well, take the derivative with respect to age. That's going to be beta 1 plus beta 2 times 2 times age. That's the first derivative of that parabola. Often we estimate that beta 1 is positive and beta 2 negative. That shows that people's age increases their wage at first, but gradually the wage increase on your birthday gets smaller and smaller. Eventually you're over the hill. You stop getting a raise on your birthday and actually start declining. We can find that peak by setting the derivative equal to 0, since that's the local maximum. Excuse me. For different signs of beta 1 or beta 2, it would be a minimum. If you like that, then add in higher order polynomials, x cubed, x to the fourth, etc. There are debates about how many higher order polynomial terms you really want. There is a limit. People debate whether to stop at x cubed or use fourth power. You can test it. You can do a joint test for whether all the coefficients on these higher order terms are jointly equal to 0. We talked about how to do that back with hypothesis testing. Now, we generally would not want to do tests one by one, maybe, drop the squared term but leave the cube. That's kind of weird. I think we'd have such precise knowledge about one of those polynomial terms and not any of the others. It's probably just an error from the test. Just as we put in squared or cube or higher polynomial terms, we can also put in logs. Now, we're not in elementary school, so log here means the natural log, base e. That's what makes sense. You could take the log of x, you can take the log of y, you could do both. Just remember Jensen's inequality, the mean of the log of y is not the same as the log of the mean of y. One of the reasons we economists often use logs is because from calculus, again, logs have an easy interpretation. In a regression where I have log y on the left, each beta is interpreted as the derivative with respect to that x variable. And the derivative of the log is the percent change, right? You remember that from principles class. If I have log x instead of x on the right-hand side, then I interpret that coefficient as the change in y from a 1% change in x, not a 1 unit change in x. If I have log x and log y, then the coefficient is going to estimate the elasticity. See? Great uses for nonlinear regression, even though it's kind of linear.